So, hello everyone, I'm Clara Guilhaumon. I'm working with AMVALOR in Paris, and I have done a secondment in UPM in Madrid from February to March to work with CoMetaS project on metamaterial issue. More precisely, it was to work on active design of metamaterial with specific mechanical properties. And so here I will present the work we have done and some results. So when we are talking about material, the main issue is to know material behavior and to know material properties, because in most of application and in most cases, we want to select materials that fit some specification. For example, in industry, you may want to select a material that is more or less hard, or a material that has a certain melting temperature for a certain application. And so you have to know which material has which property in order to select the good material for your application. With metamaterial, it's kind of different because now you have new opportunity because you can directly design the wanted material with the wanted property. Indeed, when you are constructing a metamaterial, you are starting with a cell of a material which has known properties, and you will put the cell all together in order to construct an assembly, which will be your metamaterials that will have properties that are at first unknown, but are mainly different from the initial materials that constitute the cells. So it gives you new opportunity, but now the question is how to know which assembly will give the wanted property in the end. So we work on this idea with UPM in Madrid with their knowledges about mechanical behavior and mechanics in general, and with the knowledge of AMVALOR in Paris with machine learning issue and active learning. And the question we wanted to answer is how to efficiently design a metamaterial. And to do this, we develop an efficient and automatic method to find the structure that will give the wanted property of the metamaterial. So to do so, we will use an active learning methodology, which is an iterative process to construct training database for machine learning model. And it's based on the idea that if you select at each step the best sample for your model, you will improve faster the global performances of the machine learning model. So to detail a bit, you start with a small training database, which is chosen randomly or with a small design of experiment, and you have a pool of data. So you will train your model on this few database, and you make a prediction over this pool of data. And to each prediction of the pool, you will have the predicted value, and you will add an information criteria. Then, based on this information criteria, you will select the one which has the best value, and you will add it as a training point to your database. Then you will retrain your model, and based on the hypothesis we have seen before, you will have better prediction than before. And so you will make loops of this process. And at first, the prediction of your model will be quite bad because you have few data. And you will increase step by step the database and increase the accuracy of your prediction also by adding this kind of points. And so then you stop when you have enough points on your training database according to some other criteria, some other stopping criteria. So here we will use a criterion coming from this active learning procedure to lead the search to an output value and not predict the surface of or the function all over the space. So to do this, we will mix our criterion, a criterion coming from active learning, with the distance to the objective point, and we will create a cost function defined as below that will just mix both of them, the prediction, the information contained in the prediction, and the distance to the objective point. We tested the methodology first in a two-dimensional function, which is a polynomial function, and we want to reach the objective value of 300, which is represented on the plot. And we don't know what is the behavior on the function on the other part. So we will add points step by step to reach this output value and to know which are the input x1 and x2 that correspond to an output of 300. So at first, the algorithm will put points more or less randomly. And then when we will have found an area where the output value is more or less 300, it will focus on this area. And in the end, we will see that the points are more and more are still in the area of 300. And if we look to the input parameter corresponding to the output value, we will see that we have found the area we wanted to reach. Then we increases the number of dimension of the problem, because this kind of methodology is interesting with problem with more dimension, because with 2 dimension it's easy to compute the solution everywhere, but if you have more dimension the space is wider and so it's more difficult to and more long to calculate the solution everywhere. So here we take an example with a 5-dimensional function and we want to reach the objective value of 6. So it's the same idea, we will add points step by step to reach the output value we want and not predict the behavior of the function everywhere. So we will see that at first the algorithm will put points on the border where the value is more or less close to 6 and not in the center. Here it's plotted in 2 dimensions, 5 dimensions, but we can see it just on the x, y, and x2. And then we will see that the algorithm will converge on the corner, which is in the back, where the value is 6 more or less. Then we came back to our metamaterial design, because the aim was to design a metamaterial with a certain specific mechanical property. And so here we will do the same, just we will replace the output value with the Young modulus equivalent on the x-axis. And we want to determine which are the inputs, so in the size of the macroscale cells, S, X, XY, and XZ, to put to have the wanted Young modulus. To do so, we created a code that allows us to create a structure corresponding to the metamaterial you want. So we have as input the number of cells in each axis and the dimension of each cells. Then we do a quick simulation with the stiffness matching method to simulate a tensile test. So we will apply a strength up and down and get the displacement of each node. And then a quick post-treatment will help us to determine the equivalent modulus of the structure. To have some details, for the displacement calculus, it has been done with the stiffness matrix method, so you have the matrices and the vectors that correspond to the displacement and to the calculation. And for the equivalent Young modulus, we just replace in the definition of the Young modulus with our parameter and our structure. So right now, the conception of the methodology to design the metamaterial for the active search, it has been done and this has been tested on theoretical function and it seems to work. Right now, we are currently working on the mixing and putting the metamaterial simulation inside the active search process. And because we have to fix some hyperparameter value to have good results, and we are trying to reach Young modulus on the x-axis of around 116 as a first example. Then for the further step, we would like to increase the number of inputs of parameters at the size of the cells, because as we have seen before, this kind of active search methodology works well and is efficient in higher dimensional problems, so it will be more interesting with more dimensions. And we would also like to increase the dimension of the output, looking, for example, for the whole Young modulus value, or to add more mechanical coefficients. So thank you for your attention, and if you have any questions, thank you.